Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Anicia Arredondo with us today. Hello, Anicia.
Hi, great to be here.
Well, thank you so much for agreeing to talk about your very lovely article, which we'll get to very shortly here. First of all, I got to compliment you on your posters there on your wall there. It looks like you got a dart and you got a Sophia going. So, yay on that.
Yes,
Very
thank
cool.
you.
And I gather you are somewhere around San Antonio based on that other poster. And so how is the summer in San Antonio in 2025?
It's actually great. We just got a cold front, so we're down to 90 degrees Fahrenheit.
Wow, that's awesome. Very good, very good.
Yeah,
Humidity down too?
I'm sorry.
The humidity is down as well too?
Oh yeah,
Nice, nice.
this is what I call nice
Um,
summer weather.
yeah, lovely, lovely. I should visit sometime. So it is September 2nd of 2025 as we record this, and I'm in Phoenix, and yeah, we are in our swelter mode.
Yep,
So I think it hits
familiar.
like 90 degrees at 5 a.m. in the morning, and it warms up from there. Uh,
Yeah,
it's also the wet season in Phoenix. This is when we get our most of our rain. We get the monsoons rolling in. So it's a little more humid than it would be otherwise most of the year. So very good. Um, and Anisha, what do you like to do for research?
what do I like to do for research? Mostly what I do is spectroscopy of asteroids. And so
Cool.
I'm really interested in the surface compositions of different asteroids because they're the building blocks of what formed the planets, and every single one is kind of unique. And so I want to study all of them
Cool.
and kind of piece together what the early solar system looked like and what has happened since it formed until now.
Very nice. Beautiful. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. JWST spectroscopy of 142 Polana, connection to NEAs 101955 Bennu and 1627 Ryugu. And Anicia, take us away.
Yeah, so first I just want to acknowledge all of my co-authors here. Tracy Becker, Maggie McAdam, Andy Rivkin, Stephanie Jarmek, and Ian Wong, all of which were very helpful to me as I navigate this brand new era of spectroscopy we have with JWST.
Cool. Nice little international collaboration here going on too, a little bit. Very cool. Wow, it's Cambridge, Massachusetts, not Cambridge, UK. Okay.
Yeah, it's like,
It's a very good national collaboration. Very good.
thank you.
Okay, good shout out. Okay, let's get into it.
Yeah, so basically, a lot of what my thesis work was studying asteroid families, collisional families.
Mhm.
And what those are is back when the solar system had formed, there's these large-ish planetesimals, and over time, those have smashed into each other, and they create a bunch of little tiny fragments.
Mhm.
And those fragments, because they came from one body, will have similar compositions to each other, and
Mhm.
they're also going to have similar proper orbital elements. They're orbiting the sun at kind of the same rate as each other, too.
There we go. Okay.
Um, and so we study those to one, learn about collisions in general,
Mhm.
and two, to try and, like I said earlier, piece together what the early solar system looked like.
Cool.
And so one of the biggest families in the inner main asteroid belt, which is the part that's closest to the Earth, is the Polana family.
Okay.
And the Polana family is interesting for a number of reasons. It's, like I said, one of the largest families. A lot of the family members are B types, which means if you look at their spectra, they have a downward blue slope.
Okay.
Um, it's one of the older families in the main belt,
Okay.
and it's also a really good source population for near Earth asteroids. And obviously, near Earth asteroids are interesting for, one, they might kill us.
Yeah.
Two, they offer really good opportunities for spacecraft missions because you need really low delta V to get to them.
Mm-hmm.
Um,
Mm-hmm.
and three, some people are interested in them for things like in situ resource utilization.
Oh.
Eventually, if we have companies that are going to go, mine asteroids or whatever, you
Mm-hmm.
want to know what they're made of.
Yeah.
And one of the ways you can know what they're made of or infer what they're made of is if you know where they come from. Because like I said, family members have similar compositions.
Mm-hmm.
And so if we know that a near-Earth asteroid came from a particular family, we can kind of make a guess based on what the rest of the family looks like of what that NEA is going to look like.
Cool. I'm with you. Mm-hmm.
Okay. And so it's just really lucky that the two spacecraft targets, Bennu and Ryugu, that the OSIRIS-REx mission and JAXA Hayabusa 2 mission have just gone and returned samples to and brought back. Both of those are actually hypothesized to be from the Polana family. And there's a number of reasons why people think that, one of which is dynamics. The Polana family is very near to what's called a Kirkwood gap. It's secular resonances with Jupiter. And so when near-Earth asteroids not near-Earth asteroids, sorry, when family members are orbiting, they're kind of drifting away from the center of a family at a rate that's inversely proportional to their diameter. So small things will drift away faster, and they can drift in semi-major axis into these secular resonances, and their eccentricities get bumped up enough so that now they can either be ejected from the solar system or they can come and into near Earth space.
Okay.
And so Polana family is right up next to one of those resonances. And so it also produced a lot of NEA-sized fragments because they're smallish. And so based on dynamics, we think that Bennu and Ryugu, based on their inclinations, probably came from the Polana family.
Gotcha.
And then a while back, there is a study with visible and near-infrared spectra to compare family members within the Polana family to Bennu and Ryugu. And what they found was that the spectra, near-infrared and visible spectra of both asteroids are consistent with the spectra that are found in the Polana family.
Okay. And
so that's great. But the thing about these, what we call primitive asteroids, which are unaltered by heating, they don't have a lot of spectral features in the visible and near-infrared wavelength ranges. And so what that comparison was just looking at spectral slope, which is great, but we know that these should have features in the 3-micron wavelength region, which is really hard to do from the ground, especially if they're faint objects. Yes. But luckily, we have a new telescope that's not on the ground. And so I applied for time to observe Polana because we already have 3-micron spectra of Bennu and Ryugu from the spacecraft. And also now we have it from the return samples, from laboratory analysis of the return samples. And so I got JWST observations in the near and mid-infrared of Polana. And basically the idea was to compare with the NEAs and test the hypothesis that they came from the same, from the family, basically.
Yes, very cool. I am with you.
Yeah. So that's intro. If you want to scroll.
It's good. It's great. Wonderful. Okay.
Yeah. So yeah, the observations, we used the NIRSPEC instrument, which is the near infrared, and the MIRI instrument, which is the mid infrared. And so this table 1 is showing the date, the distance from the sun to the object, the distance from us to the object, the phase angle, and then the V magnitude.
Yes. Okay.
And so all of those parameters are important when you're doing thermal modeling. So it's good to include them in papers.
Yes.
But these observations, the MIRI observations were taken at 1:14 UT, and then the NIRSPEC observations were taken at, 8 p.m. UT?
Yeah.
Yeah. And so they're separated by about 7.5 hours.
Yeah.
The rotation period of Polana is 9 hours. And so just in case there's differences on the surface, we didn't combine the two observations because enough time had passed between the two observations that we might have seen different parts of the surface.
Right.
We didn't want to accidentally stitch things together that are different.
That might be different. Yeah. Right.
Yeah.
I'm with you. Okay.
Yeah, so this part is detailing the observation and the observation modes and stuff like that.
Yep. Lots of capitals here. Mary Fulongs.
Yeah, it's fun to type.
Yeah, I bet. Very cool.
Um, yeah, so like I said, JWST is very new to all of us, and so I actually didn't do any of the data processing myself. Ian Wong from STSCI did all of it. And so these paragraphs here, I don't fully understand every single thing that they're saying. Um,
That's why you have
but
co-authors.
yeah, that's why you have co-authors.
Okay, very good. Okay. Do, do,
Um,
do, do, do. All
I think
right.
I'm missing.
Okay. Nice and
Actually,
detailed. Very good.
yeah,
Maybe we slide down to the figure one.
we can do figure one. Yeah,
Okay. Let's go and look at basically the results. Extracted fluxes. Okay.
yeah. So this is what you just get straight out of the telescope. It's flux versus wavelength.
Hmm.
On the left is going to be the near spec observations, and there's two different filters. The black one covers that shorter wavelength range, and then the red line is showing you the longer wavelength range.
Okay.
And so the flux that you get from an asteroid in these particular wavelengths is actually a combination of reflection of the sun and also thermal emission. So that's why it kind of like has
Okay.
that U shape. So
Hmm.
the yellow line is showing you the solar analog that we use to take out the solar contribution. And then what we use for the thermal contribution, there's a lot of thermal models out there, but we use the near Earth asteroid thermal model,
Uh-huh.
which is not just for near Earth asteroids, it actually works for main belt asteroids too. But so that is going to remove that tail and the red filter.
Yes. Okay. Good. I'm with you.
Yeah, and so the right is the Miri fluxes, and there's 12 different channels, so that's all the different rainbows of colors.
Ah, okay.
Um,
Gotcha.
yeah, and so that's what all of the IFU short, IFU long, all capital letters were.
Hmm.
Um, and we know that there's some issues with Miri in the very last channel, so that weird spike going up and falling
Yeah.
down probably is not real. It's probably an artifact. Um,
I'm reaching
but
the
then
end.
that black line there is the near Earth asteroid thermal model that we fit to this part of the spectrum.
Okay. Good. I'm with you.
Yeah. And so to get emissivity and reflectance, you would divide out the model, and you're left with basically just what is coming from the asteroid itself.
Cool. Okay. I'm with you. Okay.
So I don't think we're actually at table 2 yet.
Okay. That's good. Keep going down.
That for now.
Data analysis. There we go. Thermal mods.
Yeah, so thermal modeling, like I said, you have flux from reflected sunlight and thermal emission. You have to fix both of them. Yeah, that's where we describe the simple thermal model. And this was one of the original models that assumes that it's a smooth spherical body that doesn't rotate, so there's no thermal inertia, and it's observed at a phase angle of 0. And
Mm-hmm.
obviously that's not that's not feasible. Um,
We'll start.
because yeah, objects actually aren't spheres, and they do have thermal inertia, and they do rotate,
Yep.
etc. And so then the NEADM improves upon the STM
Okay.
by it adds this normalization factor called the beaming parameter. That's the eta,
Okay.
and that it's kind of like a fudge factor that is all of those thermal properties rolled into one.
Got it.
So to fit the
Yeah.
things that were in table 1, the observing geometry and such, those are the
Mhm.
inputs, and then the output is going to be the two free variables are geometric albedo, which is correlated with diameter,
Uh-huh.
and that eta factor. And so we
Okay.
fit, least squares model, picking which variables make the best fit.
Yeah, we saw that in figure 1. Yes.
Yeah.
Mhm.
Yeah, so that's how we did that. The derived values that we found are a geometric albedo, or PV, of 0.038, which is reasonable for this type of dark asteroid, a diameter of about 51 kilometers, which I
Okay.
think is pretty on par with what
Okay.
previous observations had found.
Mhm.
Um, and then the eta that we found is 1.047, which is about normal for main belt asteroids. So that's all well and good.
Good. Good.
Um, let's see. Yep. You can scroll down, I think, to the figure.
Features, you want to cover some spectra?
Yeah. Okay. So this is the near spec spectrum in purple. And
Mhm.
then the pink line is the ground-based spectrum that I mentioned earlier. And you can
Yes.
see that in the region that the two overlap, it's pretty good agreement within the errors.
Yeah.
Um, and that,
Okay.
yeah, the reddish slope there in the 1.5 to 2.5-ish range
Okay.
is actually a long wavelength end of that broad absorption feature that seems to be centered around 1.2 micron.
Yeah. Hmm.
And that might be due to magnetite, which is makes sense for something of this
Okay.
composition.
Cool.
So then the other features that I found, or we found, at 2.72, there's OH,
Yes.
which is very common on asteroids like this. It's a sign of aqueous alteration.
Hmm.
And then there's two shallower features at 3.4-ish and 3.98. And
Yeah.
those are due to a mixture of carbonates and organics or just carbonates by themselves.
Okay.
And I think one of the, if you scroll down, one of the, um, I think it's the next figure, has the continuum removed, so you can see that those are actually features. Yes, this
Ah,
one.
yes. Okay, I'm with you.
Yeah.
Let's see.
So on the left is basically what we saw in uh, the last figure, and then I show you the points that I basically just fit a 1D polynomial and divided it out to show you that the 3.4 and the 3.98 feature they're actually features there.
Yes. Yes. Okay, I'm with you. Hmm.
Yeah. And then so the width and depth of those I measured, and
Yes.
those are what the values that were in table 2, I think. We don't have to look at them though. Just,
Okay.
yeah.
Yeah, I can eyeball it from here. It's good.
Yeah.
Okay.
Um, yeah. Okay. So maybe scroll back up. Did I skip other stuff?
Sure. Let's see. Covered that.
We saw that. That's about fitting the.
Okay. Yes. Yes.
Slope
Saw
agrees with the
that.
previous slope.
We saw this. Uh-huh. Yes. Hmm. Yes.
Okay. So then I think the next thing is
Okay.
to be more quantitative.
Ooh.
We
Oh,
measured the hydrogen weight percent, which is the weight percent of hydrogen estimated. And you can do this using the shape of that 3 micron, the 2.7 micron band that I said was due to OH.
okay.
So there was laboratory work of carbonaceous chondrite meteorites where they measured the 3 micron feature and then measured the amount of the hydrogen to silicon ratio.
Okay.
Um, and they found that there's a correlation basically, and with the caveat that this is a laboratory study that isn't done in perfect space conditions,
Yes.
but for our purposes it's fine.
Hmm.
So this equation 1 is telling you the hydrogen to silicon ratio basically depends on the ratio of reflectance at 2.9 to 2.5 microns.
Okay.
So you go and you measure the reflectance at those values, you do a whole bunch of math, and then you get a value for hydrogen weight percent.
Okay. Interesting.
Uh,
Okay.
Yeah, and that's detailed in this paragraph. There's another way, which is the next equation.
Mm-hmm. Okay. So another
That
way to
equation
do
is from one
this.
paper. This equation is from another paper. Same kind of idea, though, where they used laboratory measurements of carbonaceous chondrites to establish a trend. But this one uses the band depth, which is the difference from the continuum, at
Yes.
2.75 and 2.8 microns.
Okay.
Um, And I did this because it was in one of my co-authors' papers, Andy Rivkin. He
Okay.
did this exact same analysis on JWST data of Ceres, Hygeia, and Pallas, which
Okay.
are three much larger asteroids in the main belt.
Mm-hmm.
And I saw his figure, and I wanted to see where Polana fit into it.
Good. Good.
Um,
Okay.
so I think the figure after this one is yeah,
Yeah. Here is our percent weights of H. Okay. Mm-hmm. Oh,
yeah.
lovely. Okay.
So
Nice.
So actually, most of these data points are from Andy Rivkin's paper.
Okay.
But so this is showing the derived values. The red point is from that equation 1 that used reflectance. The
Yes.
green point is from equation 2 that used the band depth. And
Yep.
then the blue point is the weighted average of the two.
Okay. Yeah.
Um, and
Yes.
also what's plotted are the hydrogen weight percents found for a number of Ci, Cm, and Cv meteorites
Okay.
from the laboratory studies.
Okay.
Um, and so Ceres and Hygeia are both C-type asteroids, so carbonaceous, as so is Ryugu. And you can see that Ceres and Hygeia values are within that Cm range, while
Yeah.
Ryugu is a little bit lower. And
It's
the
lower.
green point is actually within the Cv range, which is kind of
Mm-hmm.
weird. Pallas is a B type, that's the blue sloped. Um,
Right.
and Bennu and Polana are also B types. And
Okay.
you can see that the Pallas actually has the highest values of hydrogen weight percent of all of these objects.
Yeah.
Compared to Bennu and Polana are also low, like Ryugu, around 0.2-ish,
Mm-hmm.
and with kind of within that CV, teetering on the CV edge.
Okay.
Um,
So we're getting a hint they're similar.
yeah, so this to me says that, even though the, I guess, accepted meteorite analogs of Bennu and Ryugu are said to be Ci and Cm meteorites, maybe there's a little bit more to the story here, where they don't look like other C and B type asteroids, but they do look like Polana.
Okay. Cool.
If nothing else, I think that this figure can get me another JWST proposal if I
Oh,
play
there
my
we
card.
go. There we go.
Yeah.
Very good. Cross fingers, cross fingers.
Yep. We can move on.
Okay. Let's see. So we got this, boom, boom. We got our hydrogen. Okay, I'm with you. All right. And we can move on. And what we got here? Near spectrum.
Okay, so that was the near spectra. But we also got mid-infrared, which for asteroids, it's a very niche field, I would say, because if 3-micron observations are really hard to get from the Earth, mid-infrared observations are almost impossible to get from the Earth.
Yeah.
So we've had, Spitzer and airborne observatories and stuff that are capable of getting mid-infrared spectra, but it's the number of mid-infrared spectra that we have for asteroids is like less than 100 objects.
Okay.
So it's a new and exciting and awesome field.
Yeah.
So here, the purple is Polana from JWST.
Okay.
And let's see. So some of the features that I am positive that or pretty sure that I see are at 6 micron. There's an emissivity feature that I think is olivine.
Mm-hmm.
At 7, there's another emissivity feature that I think is due to carbonates. And then over at 22 is a dip that I think is due to phyllosilicates.
Okay.
And then 12, where I point out the artifact, that's actually caused by a light leak in the MIRI instrument.
Okay.
A light leak, yeah. So if you look at a lot of different MIRI spectra, they're all going to have that artifact there. So I just pointed it out. Don't think that that's, some new and interesting element that I just discovered.
Artifactium.
Yeah.
I do want to point out there are error bars around this purple curve.
Yeah.
Really small.
It's shaded, yeah.
Mm-hmm.
But I also am comparing it to spectra from Spitzer.
Okay.
Of other C-complex asteroids. So Ceres is the blue line, Eugenia is the yellow line, and Pulkova is the red line.
Okay.
And all 3 of those asteroids have this bump around 10 microns.
Yes.
Yes. That's very common in asteroid spectra. It's due to silicates. That's pretty much all of the mid-infrared papers we have are measuring that 10 micron feature.
Mm-hmm.
But if you look at Polana, it doesn't have it.
Right.
Which is strange.
Yes,
and I'm still trying to figure out why.
Yeah.
It is, as you go from the surface scattering to volume scattering regime, the shape of the mid-infrared spectra does change.
Mm-hmm.
But I have not seen anything that completely matches this shape, where it doesn't have a Christensen feature, really. It kind of just goes up and then stays up for a long time. Yeah.
Mm-hmm.
So this to
Interesting.
me, um, this is why I want to observe more family members in the mid-infrared, because I want to know, do they all have this? Is this like a very special asteroid that I just happened to stumble upon?
Right.
Um,
Or the common.
yeah, exactly.
Cool. Mysteries are
Um,
great. Mysteries are great.
mysteries are great. Yeah. Um,
Okay.
yeah, so that's the mid-infrared spectrum.
I like this
We can
figure.
keep going.
I like this one. Okay. Let's see. Okay, we got
That's just
Miri.
describing them. Yeah, so we can talk about the NEAs now.
Okay.
So like I said, yeah, the dynamics and the visible near-infrared spectra both have shown that Bennu and Ryugu could come from the Polana family,
Yep.
or there's another family near it called the Eulalia family.
Okay.
And there's also a background population of asteroids that don't belong to any family,
Right.
which it could also come from.
Okay.
Um, so here I'm saying kind of what I said earlier. You can keep going.
Okay. Going. Let's see. We got that. Size dependence. Okay. Dude. Talk about the low background or low
Background.
albedo backgrounds.
Mhm.
Okay.
So yeah, we'll just look at the figure then.
Okay. Figure six.
So yes.
Okay. JWST.
So
Because you got a proposal coming. Very
here,
good.
the left is the near spectrum in purple. The right is the MIRI spectrum in purple.
Okay.
And we'll just start on the left, I guess.
Sure.
I'm comparing it to the global average spectrum from the OVIRS instrument on the spacecraft. That's what the black line is.
Yes. Okay.
And then the yellow line is a relab spectrum that of the return sample, one of the return samples. So it's
Okay.
not necessarily indicative of the entire surface, but it's something.
Mm-hmm. Got a piece of
Um,
it.
and so
Okay.
right off the bat, you can see that there's major differences in the slope between 0.5 and 2.5. Um, well, Polana and the lab return sample both have red slopes that are going positive. The spacecraft spectrum has a very blue slope.
All
And
right.
so in the paper that I got the lab spectrum from, which is by Dante Loretta, the PI of OSIRIS-REx, he said that these differences could be due to something like grain size or reddening of some type. And
Right.
yeah, so, but the Polana spectrum matches better with the laboratory spectrum, which is weird because you would think it would match better with the global average spacecraft spectrum.
Right.
Yeah,
Indicating it's either a weird one or what.
something's happening, yeah.
Mm.
But if we look at features within the three, all three of them have that 2.72 micron feature
Yeah.
that is OH, but the width and the depths are different. Um,
Yes.
I think all three of them have the carbonates and organics feature at 3.4. And
Yes.
then
Agreed.
the over spectrum didn't go that far out, but the lab spectrum does look like it also has the 3.98 carbonates feature.
A little bit. Yeah.
And so, um,
Mhm.
because the multiple features are present and the slope is similar, at least with the lab spectrum, I think that's another line of evidence that these have similar compositions to each other.
Okay. Good. I'm with you.
Yeah, and then so on the right is Polana in purple again, compared to the OTES spectrum of Bennu from the spacecraft. Again, it's the global average, so it's not a certain spot, it's a bunch of spectra averaged together.
Okay.
And so these lines are pointing out what they found in their spectrum, and then I just put the line so that you can kind of guide your eye and see if it's also in Polana. So,
Right. That's the vertical.
so at 7, there's a little bump there that they said could be pyrites, vanilla, or carbonates.
Mm-hmm.
And what I figured is in Polana is carbonates. They show a very clear Christensen feature around 9 microns. And actually, if you follow that line all the way up, you could kind of see one at this something at the same spot in the Polana spectrum.
Right. It's definitely
I'm
right.
not sure if it is.
Mm-hmm.
I don't want to say this is a Christensen feature without being completely sure, but it's awfully suspicious that they look kind of similar to each other.
Okay, good.
At 18, there's actually a teeny tiny dip that they say is due to magnetite. And then if you look up on the Polana spectrum, I could convince myself that there's a little tiny dip there too.
Yeah, you could convince me as well. Okay.
Yeah. And then at 19 is a
Pyrosilicate.
bump. Yeah, that they say is due to phyllosilicates, which I could also see in the Polana spectrum.
Okay.
So I'm not committing to saying that any of these are also in Polana, but I am saying that the features that are there look relatively similar to what's on Bennu. Again, saying that maybe they came from the same place.
They're suggestive, yeah.
Yes.
Cool. Very nice. Okay.
Keep going.
Okay, let's slide on down. We talk a little bit about Bennu. Talk a little bit about Ryugu. Our discussions, differences, reasons. Okay.
Okay. So this is kind of the same thing we just talked about, but instead of comparing to Bennu, we're comparing to Ryugu. And so here, purple is Polana again.
Yes.
The gray points are from the nearest 3 instrument on Hayabusa 2.
Okay. Yes.
And then the red and the blue are both spectra of the return sample, and the difference is where on the surface they came from. So chamber A came from the first touchdown sampling, which is just the immediate surface that they grabbed.
Yes.
And then that's the red one. The blue one is chamber C, which they used, they made an artificial crater, and then they sampled that. And so that is sampling what might be subsurface material that might not have been exposed to the space environment.
Trying to get a handle on space weathering. Okay.
Yeah. So yeah, same kind of thing here. First, we look at the slope, the near infrared slope. They're all red within the errors of each other, reasonable match. All 3 of them also have the 2.72 micron feature. It's due to OH.
Yes.
But again, the depth and the width are slightly different.
Definitely.
I'm not completely. I think other people are going to figure out why, and so I don't have to. And if in another year or several years I put out another paper that says now we know, then that's great.
We'll come back to that. Okay.
Yeah. So here in the red and the blue spectra, you can see a shoulder kind of around 3.1.
Thereabouts, yes.
It's like a very, yeah. And so if you follow that line down, you could maybe see it in the Polana spectrum. That's due to ammonia. I'm not completely sure if that's actually there, though.
Yeah, subtle if it is.
The 3.4 micron carbonates feature is very prominent in the return sample spectrum. So same kind of conclusion here, that there's probably processes that are altering the shapes of the bands, but the fact that all the bands are there and kind of in the same locations, to me, says that they are related in some way.
Okay, good. And I think we got one more.
And so then because all of those last 2 figures had offsets, and if you're like me and your brain doesn't do offsets, I made another figure that just has all of them on top of each other.
There we go. Good.
So here I think you can see the comparisons of the slopes better in the near infrared region. They're not exactly the same, but they're kind of the same, to where we have processes like space weathering that we know make these amounts of differences.
Yeah.
But here you can really see the differences in the 3 micron feature. And it's not something like, Polana has just a broader feature than all of the NEAs. I think what we're learning from Bennu and Ryugu is that they're different bodies, and there's not a one-size-fit-all thing that explains both of them perfectly. And this is kind of another notch in that argument.
Yeah. So, different family members have different personalities, right?
Yeah, which could be stuff, due to where they were. Yeah, it could have something to do with like where they were in the original body. Like, say one of
Yes.
them was in the interior and one of them was on the surface, and then maybe it got the brunt of the impact and so had some heating kind of going on, shock
Yeah.
darkening, something like that.
Mm-hmm.
Or this one has been exposed to space weathering in the environment longer than this one, or something like that. There's a lot of different um, things that could explain how they could still be connected.
Okay. Okay. Cool.
I think we can keep on
Very
going.
good. Figure eight, and then we round into some. Well, we're talking about the what may cause them to be different but the same.
Yeah.
Mm-hmm. Cool.
Yeah, and then conclusions, like I said, we kind of had this idea and we wanted to use a new wavelength range to test the hypothesis that Bennu and Ryugu could have come from the Polana family.
Yes.
And based on what we saw, there were features that were in similar places, not necessarily similar shapes or strengths, um, but we didn't have, a feature on Polana that was completely not present on Bennu and Ryugu or something like that. And
There.
so, to
Right.
me, what that means is they are compatible with each other. They probably might be the same composition that just experienced different processes since the
Mm-hmm.
collision that formed the family.
Mm-hmm.
Um, yeah, and then, you always have to write that the analysis of the return samples from both of those spacecraft missions is ongoing. And so it's
Yes.
completely possible that, the interpretation of the Polana spectrum changes as we get more information from the missions.
Yeah. Okay.
Yeah.
Very cool. Very cool. Very nice. Anicia, beautiful work. And I want
Thank
to
you.
thank you for walking us through your very awesome article. Thank you.
You're welcome.
Yeah. Let's see. And you kind of touched on it a little bit on several points as we went on through. So let me go ahead and push on a little bit. Um, where do you think we go from here, given the published article? Is there anything on the horizon or maybe in the books that could further distinguish down whether it's a grain size or a space weathering? Aside from other proposals, is there additional data that could be taken? Is there more sophisticated, maybe theoretical models that could be done to help distinguish some of it? So where do you think we go from here, given the published article?
Yeah. What I really want to do is look at the smaller Polana family members and their spectra because
Okay.
Polana is, like I said, 54 kilometers, and Bennu and Ryugu are both sub-kilometer.
Right.
So I think looking at the smaller, because different processes affect different sized objects differently. So I want to look at the smaller ones and compare them and get a better grasp on if they fit in the family.
Okay.
But I also want, not me, but I want other people to do more laboratory work to understand porosity and grain size
Right.
and other asteroid relevant materials in the mid infrared specifically.
Okay.
I think JWST kind of opened up an entire new subfield, basically, of we as asteroid spectroscopists are used to having really broad features because that's all we could measure from the previous instruments. And now we have a lot of these subtle things that we don't necessarily know what they are. So I'm looking forward to more laboratory work coming out and helping me to interpret the spectra that I do have.
Very nice. Very nice. Well, it'll be really exciting to see this develop over the next couple of years, both from the sample returns and from the new instrumentation, perhaps some new laboratory astrophysics work. So it'll be really cool, really fun to see. And it's always fun to be a pioneer in a new open field. So very nice.
Yeah,
Cool.
it is fun.
All right. Anisha, thank you so much once again.
Yeah, thank you for having me.
Sure. And that'll do, everyone. And I hope this made your planetary astronomy day just a little bit better. And we will see you on the next one. Bye bye.